In section 4.6.3, we're graphing rational functions. We're going to do 2 examples in here. There's 3 pages of your notes for this section, at least if you're using the printed version of your notes. And the first example, I'm going to have you use the example from the textbook with the video from the textbook author. So you're going to go to your textbook. So go ahead and pause this video and then go to your textbook and scroll down to example 7 from 4.6. And at the end of the example 7, there's a video lesson that you can watch. And you may have already seen that in your pre-lesson. She goes really quickly through these 6 steps. So, she kind of flies through a couple of them. So it's only about a 5-minute video, but you might find that you need to pause it a little in order to be able to catch up with her and follow along with what she's doing pretty quickly. So I'd like you to follow along with what she's doing, though, and you can show your work here, and then this is where you can graph the graph. So that's the example she's going to do is this graph right here, which is a simpler example that has a vertical and a horizontal asymptote, so it's a good example. And then once you're done with that and feeling pretty good about that, then come on back to this video and push play, and we'll go ahead to do a little more challenging equation. And we'll do that one together. All right, welcome back. So now we're going to go and do this one together. And as you can see, this equation is a little more complicated. So we're just going to walk through these steps. We're going to walk through them a little slower in a more detail, though. So we'll take a little longer with this one. So we're given this rational function, and I really like to start with a factored form, not reduced, so I don't miss out on any holes or restrictions to my domain. But I do want to get it all in factored form. It's a little easier to do some calculations that way. So I'm going to factor this guy. My numerator is half factored. X plus 1 is a reduced factor. But let's see. This guy, the x squared plus x minus 2, I can reduce that to 2 linear factors. 2 numbers that multiply to -2 and add to a 1 are +2 and -1. And I have x in the denominator, then I have 2 numbers that multiply to -3 and add to -2, and that is -3 and +1. So there's a factored form, not reduced, because you'll notice I do have an x plus 1 in both the numerator and denominator. So we'll reduce that eventually, but for now, let's just leave it on there so we don't forget about it. And we'll go through these steps carefully. All right, so our first step is find the domain. So remember, a rational function is really just a polynomial over a polynomial. And polynomials, the domain of a polynomial is all real numbers. But a rational number has a denominator. So that means that we just have that to worry about that restriction of making sure that denominator is never equal to 0. So really we're just concerned about that polynomial in the denominator. So we'll set that equal to 0. So we have x minus 3 times x plus 1 equal to 0. We want that not to happen. So this is why it's important. This is one of the examples where it's important to not have the reduced form, because I want to make sure I exclude that chance that x could be -1, where I would get a 0 in the denominator, even though that would have factored out. All right, so for both the product of those to not be equal to 0, that means that both x minus 3 cannot be equal to 0, and x plus 1 cannot be equal to 0, because if either of those were 0, then that product would also be 0. So that means that x cannot be 3, and x cannot be -1. So there's my domain restrictions. And stating that in interval notation means that I go from -infinity to infinity, but I want to leave out the -1 and the 3. So it's a little messy. Let me rewrite that. Okay. So I'm going to highlight that, gather my important information so I don't lose that because I'm about to use 2 pages to do this problem. All right, so my next step is to find the intercepts. So I know if I have a y-intercept, I will only have one y-intercept because it is a function, right? So if I have the input of x equals 0, I will have no more than one y. I'm going to do this part in purple. I'm going to try to color code my steps. I meant to do step 1 in blue, so that's in blue now. So actually, before we do step 2, I want to point out in step 1, so we found 2 numbers that get excluded, right? -1 and 3 will be excluded from the domain. Those are the only 2 real numbers that are excluded from the domain. So what that means is they will either be a vertical asymptote or a whole. Because similar to a polynomial, remember, is smooth and continuous and covers all those x's. Well, if we have any restriction in the domain for a rational function, it means there's either a hole in the graph or a vertical asymptote, which we'll talk about a little more in the later steps. But for now, you can recognize that both -1 and 3 will be a vertical asymptote or a hole. Which we'll come back to that. But I wanted to point that out. So the point of me pointing that out was I want to point out that we do know that this has a y-intercept because every number that's not excluded, which we just found 3 and -1, every x value that is not excluded is part of this function. So there is a y value at x equals 0. We know that there's exactly one x-intercept on this, y-intercept, because it's a function. So if there is one, then there's no more than one because it's a function. So every time you have a function, if you put in the input of 0, you'll only have one output. So I know that there's a y-intercept because it's not restricted from the domain, and I know there's only one because you cannot have more than one y-intercept on a function. So to find it, we will set x equal to 0. And again, I'm going to use that factored form. I think that form is a little easier to work with sometimes. So I'm just going to evaluate. I'm going to this function at 0, setting x equal to 0. I get 0 plus 2, 0 minus 1, 0 plus 1, all over 0 minus 3, 0 plus 1, which equals 2 times -1 times +1 all over -3 times 1, which is, let's see, -2 over -3, which is a 2 over 3. So when x equals 0, y equals 2/3. So that tells me that there is a y-intercept. I'm going to write that important conclusion over here so I can gather my information quickly when I go to graph it at the end of these steps. And I'm going to highlight it so I don't lose it. So my y-intercept is at when x equals 0, y is 2/3. All right, going down to the x-intercepts now. Now I don't necessarily know there will be x-intercepts because a rational function could be completely above or completely below the x-axis. And I don't know how many there'll be because it's not I didn't say it was a, even though it's a function, you can still have more than one input. So the way to find out on this one is to just plug in, check, and try. So we're going to set y equal to 0 and solve for x's. And we may get none, we may get 1, we don't know yet. So I'm going to use that factored form again and set that equal to 0. So x plus 2, x minus 1, x plus 1, all over x minus 3, and x plus 1. Setting that equal to 0 and solving for x. So now that I'm solving, I am going to reduce right now because that's part of the solving process to isolate the x. So x plus 1 and x plus 1 cancel. I do want to remember, though, that x is never equals 1. That's not in the domain. I'm sorry, -1. And then I have for a fraction to equal 0, that must mean the numerator is equal to 0. So that means that either x plus 2 equals 0 or x minus 1 equals 0. Those are the two values that will make this fraction equal to 0. Solving for the left one, I get x equals a negative 2, and on the right, x equals 1. So when y is 0, x could be negative 2 or 1. So those are my two y-intercepts, or x-intercepts, I'm sorry. So my x-intercepts, my x-intercepts are the 2 points negative 2, 0 and 1, 0. So this one crosses the x-axis or touches the x-axis twice. All right, that is step 2, finding my intercepts. Let's go on to step 3. Let's see if there's any holes on this graph. So now we're reducing the fraction by factoring and cancel any common factors. So we kind of did that in the step above. So I'm just going to copy that down. And we canceled out the x plus 1. That means that x plus 1 corresponds to a hole in the graph. Remember in step 1 when we found that domain? The domain restrictions were linked to these two factors in the denominator. So this one is since it cancels, that means it becomes a hole in the graph. This one is going to be a vertical asymptote, which we will get to in step 4. But for now, we're looking at that hole. That x plus 1 corresponds to a hole. So remember, when you factor out, and when you factor, and when you cancel, when you can reduce one of those factors out, then that factor corresponds to a hole in the graph. So I have my reduced fraction with the x not equal to negative 1 because it has a hole. I would like to know what the y value at that hole would be. Like I know I have a graph here and there's going to be a hole right there. And what would that y value be? And the way I find that is by saying, well, what if I'm going to do like an alternate function instead of our actual f of x, I'm going to call it reduced function. So that's if our function was this reduced one. Let's pretend just for a moment that it doesn't have that x plus 1 there. And I can solve for, I know that at x equal to negative 1, I want to know what y would be. So plugging in negative 1 for x, gets me negative 2 over negative 4, which is equal to 1/2. So when x would equal negative 1, the y would be equal to 1/2. So that tells me, oh, I forgot to change colors again, that the hole is at x equal to negative 1 and y equal to 1/2. I kind of like to find that y value. It's not completely necessary. When you get to your graph, you could always just do the graph first and then see where the graph is at x equals negative 1 and just put a hole there. But I tend to forget to add the hole at the end. So I like to get that on my list of important information when I'm collecting. I forgot to highlight my x-intercepts. Those are important. My hole, that's important. So now I've gathered my y-intercept, my x-intercept, and a hole, so I have some things to start with on my graph. All right, let's go on to step 4. In step 4, we're looking at asymptotes. So our vertical asymptote is going to correspond to the denominator, the piece of the denominator that did not factor out, didn't go away when we reduced our fraction. So now I really want my reduced form Unfactored, I wrote unfactored here because for the horizontal and slant asymptote, it's nice. But for the vertical, actually, I'm just going ahead and leave it in factored form. So I have, honestly, it really doesn't matter which form I use at this point. But I do want the reduced form to get the asymptotes. So my x plus 1 and my x plus 1 canceled. So I'm going to go ahead and just write that, the reduced form, and remember that my x is not equal to -1. And my vertical asymptote happens when the denominator equals 0 in the reduced form. So that means that x minus 3 does not equal 0. And that tells me that x equals 3 is a vertical asymptote. So I'm going to write that over here. Vertical asymptote at x equals 3. Then I know I can put an asymptote at that line. That's an important information, so I'm going to highlight that and save that so that when I go to graph, I have that information gathered and I can throw that on my graph. All right, going on to the horizontal asymptote. The horizontal asymptote, remember we learned rule 1, rule 2, and rule 3 in the last piece of the lesson. I always use rule 2, just like I said before. I don't really like to memorize things, but rule 2 makes sense to me always. So I always use rule 2, so I'm going to go ahead and do that with you guys too. So here it is helpful to have my reduced unfactored form. So my x plus 1's canceled, and I'm left with this factor, the x squared plus x minus 2 over the x plus 1 canceled. I'm left with just x minus 3. So if I just kind of multiply those out, then I'll get that expanded form. So from that expanded form, I look at my coefficients of the highest power. The highest power here is x squared. So if I put an x squared term in there, on the denominator, it's going to have to be a 0. And that means my horizontal asymptote is going to be at, as x goes to infinity, my, this fraction goes to 1x squared over 0x squared. So that means my horizontal, 1 over 0. And 1 over 0 is undefined. So that tells me that there is no horizontal asymptote. Now, if you prefer to use all 3 rules and just look at the degree, you can do that. And on this one, you'll see on rule 3, the numerator has a higher degree than the denominator, and that also leads to no asymptote. Okay, so if there's no asymptote, that means we look for a slant asymptote. So if no horizontal asymptote, then maybe there's a slant. And we know that happens when the degree of the numerator is exactly 1 more than the degree of the denominator, which it is here. The degree of the numerator is 2, n equals 2, m equals 1. So n is exactly 1 more. That's the degree of the numerator over the degree of the denominator. Okay, so since the degree of the numerator is exactly 1 more than the denominator, I know that I will have a slant asymptote. And to find it, I look for the quotient. Remember, I don't care about the remainder. So looking for the quotient, I'm going to erase this no HA. I wrote it over here, and I want that valuable space. So I'm just going to use it for my division. So remember, I'm just going to take this fraction now and divide it. So that says x squared plus x minus 2 divided by x plus 3. And I can use synthetic division for that one because it is in the form of x minus a, where the a is 3, and my coefficients are 1, 1, negative 2. So start by bringing down the 1 and then multiply and add and multiply and add. So I have a remainder of 10, but this time I don't really care about the remainder. What I really care about is the quotient. The quotient is 1 x squared plus, x plus 4. Remember with my, actually I'm going to write that over here on my important stuff side. I forgot what I was in the middle of saying. All right, so my slant asymptote is at y equals x plus 4. Oh, I remember. I was going to say with the slant asymptote, well, we care about the quotient. The quotient gives us the line that is the slant asymptote. Okay, so now I have all my asymptotes, and on the previous page I have the intercepts and the whole, and now it is time to throw that stuff on the graph. So step 5 says to find some additional points, but it's hard to know what additional points I need before I graph. So I'm actually going to do 5 and 6 together because I'm going to start sketching it, and then as I get stuck, then I'll see what points I need to graph. All right, so I'm going to gather all my information from both pages. So I found on page 1, or not page 1, but the previous page, I found the intercepts. I found my y-intercept, and I found, 0, 2 2/3. I found the x-intercepts. There was 2 of them, one at 1, 0, and one of them at -2, 0. I also found that I had a whole at x equals -1. I actually found that it's at -1 1/2. Even if you know just the x value there, that's fine. You can just plug that in. I found that we have a vertical asymptote at x equals 3 and a slant asymptote at y equals x plus 4. And I think that's what we found through steps 1 through 4. So we'll plot that and then we'll see what the graph does. All right, so let's start with thinking about how to scale this. My slant asymptotes are x plus 4 and 3. If I leave the scale to just 1, I'm going to have problems. I'm not going to see the whole graph. So I'm actually going to scale it so that, let's see, I'm going to scale it as, I'm going to count the x-axis by 2s. Whoops, I'm going to do purple here. 2, 4, 6, 8, 10. And the y-axis, I'm going to scale by 4s, 8, 12, 16, 20. And then I'm going to plot my asymptotes, and you'll see why I did this scaling once you see. I want to make sure I get that intersection of those 2 asymptotes. I'm going to use a straight line tool. X equals 3, that's easy enough. That's just a straight line, straight vertical line. Vertical asymptote is a vertical line. The slant asymptote, though, is x plus 4. So I have to think about, where does x plus 4, it has a y-intercept of 4. So it's got a point here. And then it has a slope of 1. So if I go up 4 and over 4, I have an intercept there. Up 4, over 4. So I scaled x and y differently, so it's going to look a little different. So I have my slant asymptote going through these points. And you can always use bigger graph paper so that you don't have to scale it differently and just use ones. But now you can see why I wanted to make sure I have a little more graph on the top, because I want to get that intercept on the page. Okay, so our intercepts are asymptotes intersect here, so I'll have some graph to the left of that vertical line and some graph to the right, and I want to make sure I see it all. All right, so I also have, so I graphed these guys, that one, and now it's time to do those 3 intercepts. So at 0, 2/3, so pretty low right there. And then at 1, 0, remember this is scaled by 2, so 1, 0 is right there. And then negative 2, 0 is right there. And from there, I can actually see the this line pretty well. I can, because it's a function, so it won't, if the dots are down here in this area, it won't be over here. And it's not going to cross over that asymptote. So I can, and it will be guided by the asymptote. So the line will approach the asymptote as it gets really big or really small. So I can see those lines are guiding me to that shape right there. It's the only way to draw a smooth curve through those 3 dots and also following the asymptotes for the really large or small values. I also have a hole, so I don't want to forget my hole. I have a hole at -1. So at x equal -1, that's right about here. And I did find out that I have a hole, the 1/2, but you can always just graph it and then draw in the hole. Wherever the y value that corresponds to that x is. And you can see that I'm just going to color it in white so it looks like a hole. There. Now we got a little hole in our graph there. That's a domain restriction. That's a factor that canceled out when we tried to when we reduced our fraction, but is still a domain restriction. Okay, so the left side of x equals 3 is done. Now I have to look at the right. Now my question is the graph here or is it down here? So it's either going to be guided by those 2 asymptotes like this, or it's going to be like this, but it can't be both because it's not because it's a function. So how do I find out which one it is? It doesn't have any x-intercepts there, so I don't have any points yet, and this is where step 5 comes in handy. So when I do step 5, I say find additional points. I need the points in that area to find out if the graph is going to be up here or down here. It won't be both, so as soon as I have a couple points in that section, I'll be all set. Let's say our asymptote is at x equals 3, so I'm going to do a point at f of 4 and see when x is 4, what's y? So plugging that into our function, I'm going to go ahead and use the reduced form. I'm not worried about the -1 in our domain because we're doing 4, so I'm just going to use the reduced form. So that is x minus 1 times x plus 2 all over x minus 3. And I get, what do I get? I get 3 times 6 over 1, which is 18. So my y value, when I plug in 4 for x, I get 18 for y. So at 4, 18, there's a point right here. All right, so now I know that the curve is going to follow the asymptotes like this. I think I'm going to do one more point to make sure that that is, I don't know, just to give this a little more shape. So let's do f of 5, or you could do f of 6. I'm going to do 5 because I like small numbers. So let's do 5 minus 1, or x minus 1, x plus 2 over x minus 3, which gives me 4 times 7 over 2, which is 14. And that tells me that when I plug in a 5 for x, I get a 14 for y. So 5, 14, that's about here. So that is Using the asymptotes as a guide and those 2 points, I get that shape. All right, so I think that brings us through step 6, and we have graphed this function. Took us some time as we slowly went through each step and talked about it a lot. As you get used to this, then you'll go through those steps much quicker, and it's about a 5-minute job to do a graph. So it is still a long job to graph these rational functions, but that wraps it up. So that's our graph.